析看。
有，所以有吗？
有啊有啊。你昨天说话帮我发还有放心。
我刚早上好像有调的。
有
调镜头，
有没有确认？
哦，所以今天还是你一遍。
对。
will be given by Professor from NTNU, and he will talk about theoretical view of radical equation and check. And let's welcome.
Hi everyone. First of all, good to see you at the last day. And thank you for the organizers invitation. I'm very happy to be here again. And so in the last 90 minutes, I want to go you through a journey to the horizon scale of the Singularity Geometry series.
You can next 90 minutes. I think you're supposed to be
So we have heard from Karen's and Ria's talk about AGM effects. So now we want to go to the scale very close to the central engine itself. So we already see that there are horizontal feedback and radial feedback. But how does a Accretion Breakout system do that? So that's our focus today. So the plan for today is actually very straightforward. So first of all, to appreciate how bizarre breakout is, we will first take a look at the gravity ideas, how general relativity understand or explain gravity. And from there, we'll take a look how breakout acts as a space-time structure. However, it's a space-time structure, but it really does exist in the universe. It's really strange. And after then, we will start to hit on the road and discuss about breakout accretion and jet physics. I will first cover some basic ideas, some theoretical point of view, and then introduce some select topic from simulation inputs. So, before we get started, first of all, how do we convince ourselves the same gravitational theory can apply to both strong gravity regime and our daily life? So I would like to perform a demonstration. So to do that, I need to throw something in the air. So okay, so I will throw this object in the air several times. So please watch the trajectory carefully. Okay. So the point is, after I throw this object, it actually follow a trajectory in space-time. Okay? And actually for us, we are standing on the ground, so we are accelerated observer. So when I throw this object, so every time I throw, it can reach maybe different height, but also it takes different time. If we plot the height versus time, then it looks like this. So for the object follow trajectory in a slightly curved space-time, it takes different time to reach different height. That seems straightforward. However, we think about this. First of all, let's take into account time. And to get the unit right, we need to time times the speed of light. And we compute the curvature. And now we are actually compute the space-time curvature. We consider both space and time. And for example, for this green one and this red one trajectories, if we compute the space-time curvature, that's actually the same. So you can do this experiment at home. And the radius is about 1 light year. So that's how space-time work. And general relativity tells us some very interesting idea about gravity. So gravity is actually not a force. It's a manifestation of curved space-time. So by saying that, actually we can describe gravity as space-time geometry. And here gives an example. For this space-time geometry, I can describe a line element in this space-time. And there are time and three-dimensional spatial directions. And in front of them, there could be some coefficients. If those coefficients are constant, 1, for example, then just reduce to our flat space-time. And here is not very general, but general enough. We have some coefficient in front of time and space. And it's also important to keep in mind there's actually a minus sign in front of time direction. And this indicates time and space, their property are function of radius. For example, to the central object. So the animation here shows if we have a mass located at our coordinate center, then due to gravity effect, the radial direction will be stretched, so it's curved space. In the meanwhile, the time will run at different rate according to the distance with respect to the central object. So it's warped time. So together, in total, the curved space-time explains how gravity works. Okay, so that's how space-time should be taken into consideration. And to understand black hole and general relativity give us a lot of interesting stories. So after 1915, after a theory of general relativity had been proposed, the next year, a German mathematician found a solution. It's called spatial geometry. So essentially, just like here, so we have a mass located at the center. If we imagine the size of this mass strings, and all the way to a point, in that case, a space-time singularity will form. However, that singularity will hidden inside a space-time structure. It's called event horizon. And by this definition, event horizon is actually a space-time structure. It's not a surface. It's unlike everything we can see in our daily life. We cannot touch it. When you pass the event horizon, you just will not hit the surface. And everything once enter the event horizon, it can no longer communicate with outer universe. So this is the case for a non-rotating black hole. And if the mass is rotating, then we have another solution. So it was found 50 years later, which described a case for rotating black holes. And currently, our hypothesis is black holes, they are described by curve metric. And it's a quite, and the curve metric actually does a good job. So currently, there's no obvious deviation from the prediction of curve metric. And now, if we compare the space-time structure between a non-rotating and a rotating black hole, so there are some interesting additional features. Outside a rotating black hole, this additional structure called ergosphere. So to translate, it means there are energy stored in this region. And then the boundary of ergosphere is called static limit. And somehow we can parameterize a black hole angular momentum in terms of a dimensionless unit we call A star. So this value will remain within -1 and 1. And what's so special for this ergosphere? So it represents a region, a space-time region. Within this region, everything will be affected by the space-time rotation. So if we visualize what's going on around the black hole, let's try to shoot some photons to the black hole. And here we focus on the case those photons will eventually captured by the black hole. If we do this experiment for a non-rotating black hole, so here are the trajectories. There's no preferred directions, and all the trajectory will simply stay on the same plane. But when the space-time is rotating, as we mentioned, once the photon get close enough to the central black hole, it must co-rotate or drag by the background space-time. And this is a 3D effect. So at different locations, the photon will experience different drag. So closer to the equatorial plane or closer to the black hole, the drag is larger. Just my poor plotting skill. Should we try that? Yes. Right, and so another way to think about it, how rotating space-time works. It's like a turtle is swimming inside a fast-spinning vortex. Therefore, it's impossible for this turtle to remain static with respect to a distant tree. So that's how 3D vortex work. So the same could apply to large-scale magnetic field. So here shows, again, a rotating black hole. We have the outer event horizon here, and the yellow sphere indicates where the ergo sphere is. So for large-scale magnetic field, those red one, once they enter the ergosphere, they will be distorted by the rotating space-time. And such perturbation will propagate outward. So as a result, part of the rotational energy of the black hole is extracted outward. So this can be realized because the ergosphere exists outside the event horizon. So you can imagine that as time goes by, more and more black hole rotational energy extracted outward, the rotating black hole will slow down, and the ergosphere will shrink. And for this case, actually that's for a very few plasma environment or nearly vacuum. So if we add more plasma, the story changes. And in that case, we need to consider not only magnetic field, but also fluid. So in total, it's called GRMHD, General Relativistic Magnetohydrodynamics. And in these simulations, it's a very typical setup for the initial condition of geometry simulations. And usually it starts with a stationary torus. So without any angular momentum transfer, then this torus will just stay stationary and orbiting the black hole for quite a long time. Therefore, in order to have an accretion, we apply some initial colloidal magnetic field. And those magnetic fields are actually weak ones. And those magnetic fields will couple the differential rotation at different locations inside this torus. That's how the angular momentum can be removed outward or propagate outward. And as time goes by, accretion can take place. And one thing really interesting is black hole spinning axis is vertical in this simulation. And in this region and this region, we call it funnel region. There are few material, simply because if material want to fall into black hole from this direction, then they need to have almost zero angular momentum. And at the end, there are some turbulent, chaotic magnetic field configuration within the accretion flow. But in the funnel, there are large-scale, ordered magnetic field. So here we found something very similar. So we have large-scale magnetic field again. So there's a chance to extract black hole rotational energy and use those energy to accelerate relativistic jet. So we will see more about that later. And here we have three vectors. So that indicates the green one is the gravity due to the black hole, and the red one is the centrifugal force due to torus rotation, and the yellow one is due to pressure gradient. Because in this case, the environment, the accretion flow is actually geometrically thick. So there's an internal structure. The pressure maximum, there's a pressure gradient within this torus. So we can roughly guess the balance of these three forces. Therefore, a geometrically thick environment can be maintained. And we are also very familiar with another simple case. And in this case, we have a thin disk. So in this case, it's geometrically thin. And now, the balance is contributed by the gravity and centrifugal force only. And here, we have the case for non-rotating black hole and a rotating black hole. And we can notice there's a hole between the innermost region of the accretion flow and the black hole. So this is actually a relativistic effect. So let's consider this. So imagine at different radius, all those plasma are actually orbiting the black hole in a circular orbit. And if we plot specific angular momentum here, and for Newtonian case, it's possible to have a circular orbit at any given radius. However, for black hole, as we know, up to somewhere, the gas needs to start accelerate to a speed at which it can no longer propagate information upstream. Therefore, when they enter the black hole, they are disconnected with outer universe. Due to this argument, it's straightforward to imagine there exists an innermost stable circular orbit. Within this radius, there's no stable circular orbit. So that's why there's a hole. And the location of this east hole is a function of spin. as a black hole spin goes up, spin faster, by the help of space-time rotation, the gas can have a closer circular orbit to the black hole. So that's why the gap becomes smaller. And as we mentioned, this is a relativity effect. So, however, very interesting. If you can see this gray dashed line here, so this is a mimic to the relativistic effect. So this gentleman found that if we simply replace the Newtonian potential by this term, then we will have a curve looks very similar to the Schwarzschild one. And what's even exciting is the location of ISCO, that is the lowest point of this curve. They are located at the same location, it's 6n. And now we have this kind of picture, and we can try to estimate if the accretion starts, how much energy can be released. And to do that, so let's take a look again, where the event horizon radius is. It's 2gn divided by c squared. It's really a compact object. And in this case, if we estimate from infinity to the surface of this event horizon, how much energy can be released? And simple estimation is we can simply compute in terms of gravitational energy. If we do that, it's about half of the rest mass. But now, with this picture, we can do better. We can simply compute the energy at infinity and the energy at ISCO. And for the case of a non-rotating black hole, it's about 6%. And a very fast spinning black hole is about more than 40%. So as a result, a black hole accreting system is actually the most powerful and stable power factory in the universe. That's the physics designer Quasar. And one thing really interesting is, remembering that we have shown a numerical simulation, so we start with the torus. And such torus can actually build by applying a roughly constant angular momentum. If we do that and take a look at our specific angular momentum curve, and at where it cross with each other, actually that implies the gradient of pressure equals to 0. So there's a pressure maximum within this structure. And in that case, actually, this is on equatorial plane. So if we check the equatorial plane, and what's shown here is density. There's a pressure maximum initially inside the torus. And it's possible to build a stable torus in this way. So this is a very typical setup for the initial condition of accreting black hole, and maybe for other objects as well. Okay, and as we move on, if a gas really wants to get to the region very close to the central object, and if we compare the centrifugal force, and it's a function of the angular momentum this gas carry, and compare it with a gravity force, then there exists a barrier, angular momentum barrier. So you can imagine if the size of the central object is larger than the angular momentum barrier, then we don't need to worry about this barrier. Before the gas encounters the barrier, it's already hit the central object. But for black hole, because it's so compact, we need to worry about that. And there are different ways to get rid of angular momentum. So the first one is we already seen is by removing angular momentum outward. That's how accretion flow does. And of course, another possible way is we can form shock. So before and after the shock, the angular momentum decrease. So it's also possible for the equipping materials get rid of angular momentum in terms of shock. But in any case, if we take a look at the first picture, for example, and considering the differential rotation, closer to the central objects, the rotational velocity is faster. So this steering can interact with each other or couple with each other, either in terms of magnetic field or by viscosity. But anyhow, the plasma fitting is unavailable. So the question is, where does those energy go? And here we simply write down energy equation and try to answer this question. And here Q plus responsible for viscous heating. And we have some other terms. And this Q minus indicates the cooling rate due to radiation. And the difference between these two, the blue one here corresponds to advection cooling. So for same disk, we have seen before, actually all the heating are balanced with radiative cooling. So that's why C disk can remain same. There's no internal structure within the disk. And also, as a result, for a same disk case, the flow almost follows Campbellian rotation because the radial velocity almost equal to 0. And each radius, they have enough time to radiate their heat coming from the viscous heating. So we can imagine at different radius, actually they have a different effective temperature. And ranging from about 10 to the 5 to 10 to the 7 Kelvin. So this kind of picture is very successful for explaining luminous quasar, cipher, and Breakout Rate binary in thermal high soft state. And later on we will meet Breakout Rate binary several times. So here, just let me quickly explain the jargon here. Here the height means accretion rate. So that means the accretion rate is high. And soft behind means the spectrum is softer compared to another state. So usually we call it high soft state. And also in Yuan's talk yesterday, we have seen that for a lot of AGMs, there's a big blue bump. And such big blue bumps are well explained by the contribution of a same disk. And the low emission and a low frequency here is contributed by outer torus, dust torus. And if we move on to another extreme case, the heating is mostly balanced with advection cooling. And in that case, we have a radiatively inefficient accretion flow. And in this regime, there are actually two possible realizations, an optically thin case and an optically thick case. When the environment is optically thin, or the accretion flow density is very, very low, in that case, it's almost collisionless, including the collision between ion and electrons. In that case, viscous heating to ions cannot get rid of afterwards. So lost heat stay with the ions. However, for electrons, they can not much lighter and they can emit radiation and cool down. So in that case, we have a two-temperature accretion flow. And for ions, its temperature is roughly equal to virial temperature. So those low luminosity accretion flow can explain why some AGMs they have low luminosity. So there are low luminosity AGMs and also breakout Rate binaries. And now we have accretion rate is low, and spectrum is relatively hard state. So we call it low hard state. So another possible realization is if the environment is artificially thick. And in that case, we have a very dense environment. So the radiation emitted from the electrons cannot propagate outward, cannot propagate outside the torus. So they are trapped inside, or we call it photon trapping. So in that case, most of the heat they are still stored within the accretion flow. So we need to rely on advection again to take care of the energy balance. And for those events, they can explain, for example, tidal disruptions or ultraluminous X-ray binaries. And of course, as a side note, there's another possible choice. The flows, they are radiation inefficient, and they can choose to go outward. They can become winds. So let's call them ADLs. So Jamie also mentioned that in his talk yesterday. So if we remember there's a big blue bump for thin disk, then what's a feature for optically thin ADF? And here we are especially interested in optically thin case because in that case we can see breakout shadow. And luckily for primary EHT targets, M87 and CJ8 stars, they are optically thin ADF. And the feature is there's no longer big blue bump, but instead the bump is located at sub-millimeter. And if we take a look at the typical temperature for ion and electrons, so we have mentioned that there are two temperatures. The temperatures are different. For ions, it's roughly 10 to the 11 Kelvin, and for electron, it's 10 to the 9 Kelvin. So compared to the case for a thin disk, ADF can contribute a harder component in the spectrum. So that's why we have accretion is lower, but the spectrum is harder in state. It's consistent with our explanation for breakout X-ray binary. So that's one takeaway. And the other takeaway is here, if we check the energy balance equation again, the radiation active cooling can now divide it into three parts. So radial band is mainly due to synchrotron radiation. And EHT observation frequency is about several hundred gigahertz. So it's actually synchrotron emission. And at higher frequency, we have inverse content emission. And X-ray band, we have brainstorm. So that's why there's roughly three peaks here. And now, to move on, we want to pin down how we can define accretion rate. And to do that, we need to take into account breakout mass. So first of all, we can check the anti-internal luminosity. So I guess all of you are familiar with this. And the anti-internal accretion rate can be defined in terms of we divide anti-internal luminosity by some efficiency. So the energy conversion efficiency here is typically assumed to be 10%. By doing that, we reach this formula. So now, if we take a look at the effect of different breakout mass, and let's take the ADF spectrum, for example. And here it shows the ADF spectrum from a semi-elliptical ADF model. So again, we have a synchrotron, contact scattering, and breathstrom, and contributing at different wavelengths. And as the accretion rate increases, the source becomes brighter. But we can make the source brighter in another way. We can make the central object more massive, but keep the same editing accretion rate. But when we do that, the spectrum not only going upward, but also leftward. So that's something to think about. Now, we have a definition for the occlusion rate. Then we can plot what we have mentioned in this plot. In terms of accretion rate, editing accretion rate, when the accretion rate is below around 1%, then we have an optically thin edge or hard accretion flow. And when the accretion rate is very high, we have the optical thick AF. And it also has a name slim disk. And in between, before the editing accretion rate becomes 1, we have a thin disk. And as mentioned in Jamie's talk, and many more observational hints, this kind of classification is not global. So it's possible to have a combined disk. At this radius, it belongs to certain type of accretion flow. At outer radius, it belongs to another type of accretion flow. For example, yesterday, Johnny mentioned from method measurements, we can almost confirm, for example, in this system, NGC 4258, there's kept rare disk. However, from spectrum indications, they also require some hard accretion flow. So there's some indications. Those kind of combined disks really exist in the universe. And also from Holger's talk, we already learned about from Breakout Rate binary systems. And those systems are especially interesting because they're relatively low Breakout mass, so the dynamical time scale also much shorter than supermassive black holes. So it takes about weeks for them to change spectral state. So we can observe the same accreting Breakout system, but watch them switching the different observation, the spectral state. For example, this plot, at the left-hand side, we have a low hard state. And from on the right-hand side, we have low hard state. On the left-hand side, we have high source state. And when the accreting systems change states, the spectral behavior indicates the accretion value also varies. And here, the blue component indicates the optically thin ADF, and the red component indicates the thin disk. So if they have a combined structure, the optical thin disk is located closer to a black hole, and the thin disk is located relatively outside the black hole. And what's really interesting is there's a jet line here. Beyond some spectral states, there's no radio emission. Or to interpret that, there's no jet. And this is really interesting. So at very low accretion rate, we have jet and wind. And at very high accretion rate, we have jet and wind. But in between, maybe no jet. And maybe some very weak wind. So we have introduced some accretion flow theory based on a theoretical approach. However, the best theoretical approach can achieve is only highly integrated studies. However, in order to understand jet and wind activities, you will need more than 1D studies, and simulations are therefore needed. And as we mentioned, at very low accretion rate, it's radiative inefficient. In that case, we can simply ignore radiation feedback and simulate the system in terms of GR and HD. If we want to model the environment for a slim disk case, because the accretion flow is radiation pressure dominated, Therefore, in that case, radiation feedback is essential. So in that case, GR radiative MHD is needed. And you can expect that it's relatively easy to start with the simulation for optical sync at that case. So that's how people started. So now, from now on, we will focus on the case optical sync at that case. And the approximation is, for this kind of system, we can just ignore the radiation. So the system becomes very simple. So we consider a perfect fluid, and we consider magnetic field. So we can write down a stretch energy tensor and compute the equation motion and just let it evolve. And everything takes place in the background per space-time. That's how this numerical simulation works. And because the radiation is ignored, so there's actually no physical characteristic length scale. As a result, we can run the simulation first, and then specify Breakout mass and accretion rate later. After we specify Breakout mass, for example, the length scale is fixed. Here, M corresponds to the mass of the central black hole, and also the time scale is fixed. And we need to have another constant to renormalize the accretion rate. And this area has actively developed since around 2000. And it's straightforward to start from one fluid simulation. That is, in the simulation, there's no distinction between electrons and ions. It's just one fluid. So we have seen.
Do you see jets in that simulation?
Yes. All the time.
The density is very low.
Yes. So
we still collect jets.
yes.
So the high field on the best.
Originally started from magnetic
Thank you, Kevin. Yeah. So we have seen that after the accretion system reaches a stationary state, there are large-scale open field lines formed near the boundary regions. And actually, such magnetic field configuration is independent of the initial magnetic field. For example, we have introduced this case. So initially, we put some toroidal magnetic loop within the torus, and this is the end result. So we can consider another different initial condition setup. We have initially large-scale open magnetic field lines. They are gradually dragged in by the occlusion flow. So in the end, the final output looks just very similar after both systems reach stationary state. And also, there are some takeaways for the magnetic field configuration at different parts of the occlusion environment. So here we have the magnetic field configuration within the main body of the occlusion flow. It's mostly toroidal, and also mostly toroidal in the coronal region. So it's between the main body and the funnel regions. And the region very close to the black hole, or people call it argent regions, also mostly toroidal. As you can imagine, due to space-time rotation, so gas just need to rotate very fast, and they drag magnetic field lines with them. So that's why it becomes toroidal. And as the story changes, if we focus on the region at the funnel region, it's mostly poloidal. So there's large-scale magnetic field lines. And we are really interested in large-scale magnetic field lines. So as we introduced before, large-scale magnetic field lines, they can extract black hole rotational energy outward. But now, plasma also plays some role because now the environment is not vacuumed. So you can imagine under ideal MHD conditions, those plasmas loading onto the large-scale magnetic field, and also at those regions is magnetically dominated because there are very few plasma. The density is very low there. So the motion is mostly determined by the magnetic field instead of plasma. So in that case, consider you are in a co-rotating frame with the large-scale magnetic fields. And the plasma will experience two different forces. One is the gravity force along the magnetic field inward, and another is magnetocentrifugal force due to the rotation of large-scale magnetic field and its outward. So it's a competition between these two forces. If the gravity force wins, the plasma will streaming along the large-scale magnetic field and become an inflow. If the centrifugal force wins, then the plasma will get outward. So this is a very unique feature for GRM distillation. Inflow and outflow, they actually share the same field line. So it's again between gravity and magnetocentrifugal force. And this is actually how Bremford-Zia process really realized. So in this case, we have not only magnetic field, as we have seen in a movie a few minutes ago. So in that case, we have large-scale magnetic field. And here, if plasma comes in, plasma will play the role that they tend to deposit their rest mass energy into the black hole. Therefore, if we have too much plasma in the funnel regions, then too much rest mass energy of the plasma stored to the black hole. In that case, black hole rotational energy cannot extract it outward. So the condition for a magnetically dominated funnel region is necessary to extract black hole rotational energy outward. However, such condition can be easily realized almost for every simulation if given that the black hole is spinning. So that's a story on the right-hand side. And here is a log-scale plot up to 10 to the 4 RG. And we have inflow, outflow, and what separate them we call separation surface. And for MHD, there are 3 different characteristic speed. We have L1 speed, slow magnetosonic speed, and fast magnetosurface speed. Then, once the flow velocity exceeds those speed individually, then we can define where those surface is. So the same thing those 3 surfaces also exist for the inflow part. So there's a story for outflow and a story for the inflow. And one thing when we really want to build on semi-Newton model, then we need to take care the outward energy flux should be continuous in both the inflow part and outflow part. And on the left-hand side is a cartoon, roughly shows an environment at the horizon scale around the black hole. And here we have magnetic energy divided by the rest mass energy. And this beta is plasma beta. It's a ratio between gas pressure and magnetic pressure. So again, near the funnel region, is magnetically dominated. The ratio between their energy is larger than 1, and plasma beta value is low. And from simulations, we can also check the acceleration from accreting black holes. So it turns out MHD can help to accelerate the relativistic jet. However, it takes time. So for relativistic jet, so they're not like a gunshot. They are not starting with a high speed and then slow down. It's like it starts with a zero speed. As we can imagine that as the separation surface, the radial velocity is zero because it's separated inflow and outflow. And starting from roughly zero initial velocity, then it speeds up. And then on the way towards to infinity, it's actually experiencing the conversion from magneto energy to kinetic energy. So as a result, those plasma, they are accelerated. And we can do the same thing and check many interesting magnetosphere properties. And here is an attempt to quickly simulate the region within a fauna. And as we mentioned, the stagnation surface is roughly coincide with the location where the magnetocentrifugal force balances the gravity. As a result, it's a function of Breakout speed. So whether or not, from future observation, we can tell where the stagnation surface, if there are some energetic particle injected from there. Then, if so, then it would be very exciting. And from there, we can probably confirm or constrain what's the Breakout speed. And from the talk before, so we already have seen a lot of field are complicated. So here the same. If we simulate what's going on on those large-scale jets, and if we focus on the boundary between the jet and this wind, then there are some turbulence, there are some instabilities. So there will cause some additional loading of those jets. And to do this, we need to perform a large-scale geometry simulations. So it's presently possible by GPU-accelerated geometry code. So, so as time goes by, technology improvement will help us to explore more direction as well. And this is one example. And also shows how complicated our story could change just due to the environment and the physics are complicated. So now let's take a look at wind. I think Jenny and also Holger mentioned this. And so in this plot, it shows the analysis for a force. So the force are divided into centrifugal force due to the rotation of the gas. So in that case, all the red arrow, they are pointing outward radially. And we also have this yellow one, so it's magnetic pressure gradient. And we have the green one, the gas pressure gradient, and also the one due to gravity. So they are all pointing towards the direction of the central engine. So for this case, the Breakout speed is equal to 0. And as Breakout is not spinning in this case, so the major force drive the jet is mainly due to the pressure gradient at the center. So as the simulation goes on, more and more magnetic field accumulate near the central region. So the magnetic field pressure will become larger and push outward. And for the wind, now it's a complicated story. So it's a combination of many different forces. But still, we can see at the corner regions, we do have some winds. So, and actually winds are general quantities from hard flows. And by this study, it suggests the rate, the wind rate is roughly proportional to the central accretion rate times R with some index x, and s is roughly equal to 1. So its contribution probably not negligible. And geometry simulation brings a lot of surprise. So here's another one. So if we check how much energy, how much materials are accreting to the black hole and provide accretion power, and then we compare that with the jet power. Very strange. The jet power for some system, especially for high-speed accreting black hole system, sometimes can be larger than the input. So if the output is larger than the input, it indicates the central engine plays some role here. And here shows the simulations by Tchaikovsky. So in this simulation, what we want to focus on is the efficiency. So it's the ratio between the jet power and accretion power. But what's really interesting is it can be beyond 100. So what's going on? And the second panel here shows how much magnetic flux accumulate near the black hole. And the top panel here shows the accretion energy. So we look at the movie and notice that there are actually two curves. They share a very similar profile. So that is the middle one and the bottom one. So it turns out if we are able to accumulate a large amount of magnetic field, and as we introduced before, the idea of a reinforcement process is to extract gravitational energy outward, and it's related to black hole spin square, and also how much magnetic flux accumulates at horizon is also a square. So if we have large amount of magnetic flux accumulate onto the black hole, then we can actually extract black hole potential energy very efficiently. And it turns out we can have an output much larger than the input. So from here, maybe we will guess, if so, then why not we just keep increasing large-scale magnetic field? Just keep feeding the accreting system more and more accretion flow with magnetized magnetic fields. But the answer tends to be no, we cannot do that. The reason is there is actually an upper limit. If the accreting systems carry too much magnetic fields, so eventually such large magnetic field will truncate the accretion, then all the accretion stops. Therefore, it actually exists an upper limit. So if we define the magnetic field flux in this way, theoretically we can derive the value of the upper limit. Near this upper limit is called magnetically arrested disk. So one example is magnetic field configuration is shown on the right. So we can compare that with the case if there are not so many magnetic flux accumulated at the event horizon. So we can see the difference quite obviously. So if we have a lot of magnetic flux. And those magnetic flux will play some role to shape, for example, the disk height of the accretion flow. And even more, it should be a 3D structure. So here just shows a cross section. But in 3D, there should be some magnetic islands distributed, maybe randomly. And the plasma should find a way to enter the central energy. So there are some, for example, magnetic relativity instability for them to take place in order to make this accretion happen. So more dynamic and also more energetic in this regime. And eventually, we want to combine with observations. So far, we haven't introduced the bridge between numerical simulation and what we can really observe. And to do that, we actually need to consider, as we mentioned before, synchrotron radiation. So for synchrotron radiation, we need to know the environment, including the magnetic field strength, the local density, and the energy distribution of the electrons. And for the first result, actually, as an example, there is a simulation library, but there are one fluid simulations. In that case, we actually don't know how electron temperature should be, because we only have the information from simulation, and it's one fluid. So these are unknowns, and we know that. And there are some possible way, for example, more computationally expensive simulation to add two fluid simulation, but it's just too complicated. However, we do know the plasma heating should take place more efficiently at a region where beta is lower. So here is a definition of plasma beta again. So it's a gas pressure divided by magnetic pressure. So when the plasma beta is low, that means we have a more magnetically dominated region. So that region, as we have seen before, usually located near the axis, near the boundary region. We have lower beta. And near the equatorial plane, we have higher beta. So take this physical motivated argument. And one way to parameterize this is we can control the ratio between ion temperature and electron temperature by using different ratio when plasma beta is high. So that's why we call it ratio when plasma is high. But those are details. One thing to take away is, given that near the equatorial plane, at those regions we have higher plasma beta. So if we change the R high ratio, we are actually change the flux contributed from the equatorial plane. However, from observation, the requirement is the total flux should be consistent with observed flux. So when we normalize everything to fit the observed flux, and if we check the dominating emission regions from numerical simulation, it actually indicates they are contributed from different regions, just due to different plasma heating location in the parameter space. So these are unknowns, but that's one way to deal with these difficulties, and also indicates one future directions people should spend more effort on. And also in this picture, as we mentioned, we care about electron temperature. That's because we assume the electron energy distribution is described by relativistic mass gradient distribution. So those are thermal electrons. However, it's very likely emission are contributed by non-thermal electrons. By saying non-thermal electrons, I mean the electron density distribution for the electrons. They actually have an energy distribution, for example, as a power law. So those high energy or energetic electrons can be excited by, for example, magnetic reconnection or turbulence. But those effects are so far not included. However, there's one possible approach as we did in PhD paper 5. So these are known unknowns, and it also indicates a lot of theoretical work can be improved in the future. And also, we have mentioned one fluid approach, one fluid simulations. And in this community, people can do much better now. So there are two fluid simulations. By saying two fluids, we're talking about ions and thermal electrons. So in that case, we don't need to assume electron temperature and ion temperature. We just simulate both species, and we can compute the final image accordingly. But still, in that case, non-thermal electrons are also not included. And there are also three fluid simulations. So by saying so, we mean we have ions, thermal electrons, and non-thermal electrons. But those non-thermal electrons in this case are really given by hand, given that we actually don't have a good idea about how those non-thermal electrons should be injected. So
what is the criteria, or like how do you decide how much non-thermal electron or positron should be there?
It's free parameter. Yeah, maybe a few percent of thermal electrons. But the question is, where should we put those? Where should we inject those non-thermal electrons?
And then
I think they inject everywhere. Yeah.
Acceleration.
Right.
Yeah.
Right.
So there could be some clue or hint. Right. Yeah.
Right. So people are working on this, and
but what's the difficulty of getting like more realistic setup for this component, in your opinion? Why people just put by hand and everywhere instead of like Changwang says, like be motivated this way?
So essentially, those physics, they are beyond geometry. Some microphysics should be included. So maybe some peak simulation, which will give us some idea about under which condition non-thermal electron should be generated, and what's the spectrum in terms of energy for those non-thermal electrons. So
some people have discussed magnetic connection like within the photon, right, for accelerating particles. But now there are other mechanisms that's responsible for the non-thermal conduction, like near the equatorial plane. What other acceleration mechanisms there could be?
to
In
be honest,
addition to magnetic reconnection, I would expect magnetic reconnection to happen within the
Yes.
photon, but not near the disk. Yeah, so do you know what's responsible for possible acceleration near the disk?
that's some ongoing work, and so as I know, so there are some resistive geometry. So in that case, we can allow more realistic magnetic reconnection to take place, and from there, we still need another connection. If the magnetic reconnection takes place, then how many non-thermal electrons are generated, and what's the spectrum? So it's like I think it's like a step-by-step approach. approach and it's ongoing.
So it means there still could be magnetic recognition within the disk.
Or within the disk?
Within the disk.
Yes,
If there are some.
I think so. Those, I think, like our sun, it's kind of relatively small scale magnetic reflection, the corona heating thing, that can similarly happen to the disk.
So it also depends on how do you mean inside the disk.
I mean, within the funnel or outside.
Oh, outside, yeah. Yes, outside. And also, so between the boundary between the wind region and funnel region, there are some complicated terms, instability techniques. So this is my last slide before the final remarks. So one thing we should really think about is tilted disk. So there's no reason to expect all the accreting breakout systems, they are aligned. So in general, it's possible at large scale, the gas, they're falling towards to a black hole in a direction.
This will hang up. No, I
Almost. Yeah, in a direction means aligned with the black hole rotation. However, close enough to the black hole, such misalignment will be removed, so it will align again. However, in such case, the accreting gas will not fall into the black hole smoothly. There will, for example, plugging stream, and very possible there will be standing shock. So it depends on the inclination angle between the rotational axis of the accretion flow and the rotational axis of the black hole. So if this really happens, and if we can resolve the horizontal scale of such accreting black hole system, there should be some indication in terms of image. So that's something exciting. So we have finished our journey to the horizontal scale of the central engine of AGN. So what's so interesting about black hole accretion? So first of all, accretion type is a very interesting system as function of accretion rate. So they are related to plasma physics and energy balance. And the central engine is also the source of relativistic jets. And from there, some not so fast, but maybe important enough component, wind, can take place. And we also see from observation, there's some indication for the disk jet offering. And from, we have accretion physics, we have jet physics. That's how we try to understand AGN feedback can take place. And also, we also learned black spin and magnetic field, they matters. And simulations always bring some surprise. And an analytical model can bring us deep insights. So input from microphysics or subgrid physics is needed. So very similar to what Carol has mentioned before. Subgrid physics always needed. And there are some more additional physics beyond horizon scale. For example, on the way for the jets coming out from a region very close to the black hole and to, for example, megaparsec scale. So on the way, there could be more mass loading, there could be some injection of energetic particles. We are almost sure about that because from radio observations, those jets, they are contributed by non-thermal emission. So what's going on in between from horizon scale to large scale? So we really need to explore that And also, jet acceleration is also interesting. So that depends on how much energy budget for a geometry flow initially have, and also what's the energy conversion in efficiency along their way, propagate towards to large scale. And now with EHT and also gravitational wave efforts, we have really entered a multi-messenger era. We are heading a golden age of black hole astrophysics. And you remember Yan-Chen's talk? We are also entering a golden age of transient astronomy. So we are entering a golden age of astronomy in general. So the takeaway is for students, there are a lot of opportunities for students, also in Taiwan. So I hope together we can grow together and help Taiwan together. Thank you.
We have some time for questions and comments. Yes, please.
So regarding the magnetic field, I wonder in the simulation, what is the origin of the magnetic field? Is it charged particle, or can we learn about the origins of this magnetic field from simulation?
Origin of the magnetic field.
Origin of the magnetic field. So we have seen the case. We can initially put some corridor magnetic loop within the torus. So it's kind of artificial. However, we have also seen another case which will result in a very similar final output, that we have large scale magnetic field. So probably in reality there's something in between. So we have large scale magnetic field that dragging from larger radius to shorter radius towards the black hole. And maybe some disk dynamo can take place within the occlusion.